Hey, these are the 6.3 and 6.4 notes, page 6. So ignore the little graph at the top. That goes with the page above. I'm not sure why the spacing is off. But we're going to talk about transformations of logarithmic functions. And so here, this green graph is the same as what we graphed up here. It's the common log of x, so it's log base 10. And so let's talk about what we have here. So I'm going to rewrite this as log of x minus 2 plus 3, and then add the reminder that this shifts our whole graph 2 to the right, and this shifts our whole graph 3 up. So I'm going to start by moving the asymptote. So let me draw that in here for our original logarithmic function, our common log function. There is my asymptote. And so if my whole graph gets shifted 2 to the right, that means my asymptote gets shifted 2 to the right. My x-intercept there, that 1, 0, is going to go 2 right and up 3. Again, it's only 1 off the asymptote. My other point right here, this 10, 1, 2 right, up 3. And then we're going to draw this in. Just like the exponentials, it's a little hard to figure out how a logarithmic graph has been transformed. Just got that long towards positive infinity, and there's not really a whole lot to identify individual points. So example 5 here, we want the asymptote of the function, log of x plus 3 minus 4. This shifts everything left. So that's going to include my asymptote. So my asymptote is going to move from x equals 0 to x equals negative 3. We got example 6 here. We want to know if a and b are positive. Which of these potential equations are an accurate model for our graph? So the top two are exponential. We know that's not it. Bottom two, we've got that log function. Looks like my asymptote has been moved 2 to the right. So that's going to give me an x minus 2. And so we're looking at C here because it says A and B are positive. Okay. And so we have got one last problem that would be on page 6, so we are going to continue. I'm going to assume that this is what your copy looks like. We've got the function y equals the common log of x plus 2, all minus 2. We want to know what the x-intercept is. So the x-intercept is where our y is 0. So I'm going to put that work up here. So 0 equals log of x plus 2, all minus 2. 2 equals log of x plus 2. Again, this is a common log, which means if we do not have a base, this is base 10. So I'm going to write this as 10 to my exponent, which is 2, equals my argument here, x plus 2. I'm going to subtract 2 from both sides. I get x equals 98. 10 squared is 100 minus 2. So our x-intercept is 98, 0. Our y-intercept is where x is 0. So for b, we got y equals the common log of 0 plus 2, all minus 2. And for this we're gonna need to use a calculator. Off the top of my head, I do not know what the common log of 2 is. So once we plug that into the calculator, we know we had used 0 for x, and we get a negative 1.7 for y. As x approaches infinity, y approaches... Good question. Let's take a look at what our graph looks like. So think about the standard log function. This has moved everything left 2. This has moved everything down 2. So here's my asymptote. Left 2, down 2, somewhere down. And we know that this crosses at 98.0, so we know that it crosses somewhere. And it's rising very slow, but it does continue to rise. So as x approaches infinity, our f of x or our y approaches infinity. And as x approaches negative 2, keep in mind x is approaching negative 2 from the right, y is approaching negative infinity.